Hey everyone, welcome. I am Amjith, and today I am gonna share with you architecture of automation system, the automation pyramid. Industrial automation systems are very complex, having large number of devices with a number of technologies working in synchronization. In order to know the performance of the system, we need to understand the various parts of the system. Industrial automation systems are organized hierarchically. Various components in an industrial automation system can be explained using the automation pyramid. Here, various layers represent the wideness, in the sense of of devices, and fastness of components on the time scale sensors and actuators layer. This layer is closest to the processes and machines, used to translate signals so that signals can be derived from processes for analysis and decisions, and hence control signals can be applied to the processes. This forms the base layer of the pyramid, also called level 0 layer. Automatic control layer. This layer consists of automatic control and monitoring systems, which drive the actuators using the process information given by sensors. This is called as level 1 layer. Supervisory control layer. This layer drives the automatic control system by setting target, goal to the controller. Supervisory control looks after the equipment, which may consist of several control loops. This is called as level 2 layer. Production control layer. This solves the decision problems like production targets, resource allocation, task allocation to machines, maintenance management, etc. This is called level 3 layer. Here most of the operations are performed by humans with the aid of tools that help people to perform the production control functions. Enterprise control layer. This deals less technical and more commercial activities like management of supply, demand, cash flow, product marketing, etc. This is called as the level 4 layer. The spatial scale increases as the level is increased. For example, at lowest level a sensor works in a single loop, but there exist many sensors in an automation system which will be visible as the level is increased. As the level increases, the number of devices controlled by the layer increases. Each device in sensor and actuator layer is dedicated for a small area, but as the level increases, the area controlled by each device increases. The lowest level is faster in the time scale and the higher levels are slower. The aggregation of information over some time interval is taken at higher levels. From level 2 upward, it is not true that computer-based automation is needed or present for functioning the performing on that level. Some functions may be done by human being. All the layers are connected by various types of communication systems. For example, the sensors and actuators may be connected to the automatic controllers using a point-to-point digital communication, while the automatic controllers themselves may be connected with the supervisory and production control systems using computer networks. Over the last decade, with emergence of embedded electronics and computing, standards for low-level network standards, CAN bus, field bus, etc., for communication with low-level devices, such as sensors and actuators, are also emerging. Functional elements of industrial automation. An industrial automation system consists of numerous elements that perform a variety of functions related to instrumentation, control, supervision and operations management related to the industrial process. These elements may also communicate with one another to exchange information necessary for overall coordination and optimized operation of the plant or factory or process. Layer 0, Sensing and Actuation Elements. These elements interface directly and physically to the process equipment and machines. The sensing elements translate the physical process signals such as temperature, pressure or displacement to convenient electrical or pneumatic forms of information, which can be used for analysis, decisions and finally, computation of control inputs. These computed control inputs, which again are inconvenient electrical or pneumatic forms of information, need to be converted to physical process inputs such as heat, force or flow rate, before they can be applied to effect the desired changes in the process outputs. Such physical control inputs are provided by the actuation elements, industrial sensors and instrument systems. scientific and engineering sensors and instrument systems of a spectacular variety of size, weight, cost, complexity and technology are used in the modern industry. However, a close look would reveal that all of them are composed of a set of typical functional elements connected in a specified way to provide signal in a form necessary. A sensor system is shown, decomposed into its major functional components, along with the medium in which the measurement takes place. The physical medium refers to the object where a physical phenomenon is taking place, and we are interested in the measurement of some physical variable associated with the phenomenon. For example, the physical medium may stand for the hot gas in a furnace in the case of temperature measurement, or the fluid in a pipe section in the case of measurement of liquid flow rate. The sensing element is affected by the phenomenon in the physical medium either through direct or physical contact or through indirect interaction of the phenomenon in the medium with some component of the sensing element. For example, a thermocouple probe has the sensing element that often comes in physical contact with the hot object, such as the flue gas out of a boiler furnace, or an optical pyrometer which compares the brightness of a hot body in the furnace with that of a lamp from a distance through some window and does not come in direct contact with the furnace. In the more common case where the sensing element comes in contact with the medium, often some physical or chemical property of the sensor changes in response to the measurement variable. This change then becomes a measure of the physical variable of interest. For example, change in resistivity due to heat in a resistance thermometer wire, or generation voltage in a thermocouple in response to a difference in temperature between its two ends. The signal conditioning element serves the function of altering the nature of the signal generated by the sensing element. Since the method of converting the nature of the signal generated in the sensor to another suitable signal form, usually electrical, depends essentially on the sensor, individual signal conditioning modules are characteristic of a group of sensing elements. For example, an RTD whose output responses a change in its resistance due to change in temperature of its environment. This change in resistance can easily be converted to a voltage signal by incorporating the RTD in one arm of a Wheatstone's bridge. The bridge therefore serves as a signal conditioning module. These typically involve analog electronic circuits that finally produce electrical signals in the form of voltage or current in specific ranges. The signal processing element is used to process the signal generated by the first stage for a variety of purposes, such as filtering, to remove noise, diagnostics, to assess the health of the sensor, linearization, to obtain an output which is linearly related with the physical measure, and etc. Signal processing systems are therefore usually more general purpose in nature. The target signal handling element may perform a variety of functions depending on the target application. It may therefore contain data, signal display modules, recording or storage modules, or simply a feedback to a process control system. For example, a temperature chart recorder, an instrumentation tape recorder, a digital display, or an analog to digital converter, ADC, followed by an interface to a process control computer. Modern sensors often have the additional capability of digital communication using serial, parallel or network communication protocols. Such sensors are called smart and contain embedded digital electronic processing systems, industrial actuator systems. Actuation systems convert the input signals computed by the control systems into forms that can be applied to the actual process and would produce the desired variations in the process physical variables. In the same way as in sensors but in a reverse sense, these systems convert the controller output, which is essentially information without the power, and in the form of electrical voltages, or at times pneumatic pressure, in two ways. Firstly, it converts the form of the variable into the appropriate physical variable, such as torque, heat or flow. Secondly, it amplifies the energy level of the signal manifold to be able to cause changes in the process variables. Thus, while both sensors and actuators cause variable conversions, actuators are high-power devices while sensors are not. In most cases, Actuators are devices that first produce motion from electrical signal, which is then further converted to other forms. The electronic signal processing element accepts the command from the control system in electrical form. The command is processed in various ways. For example, it may be filtered to avoid applying input signals of certain frequencies that may cause resonance. Many actuators are themselves closed feedback controlled units for precision of the actuation operation. Therefore, the electronic signal processing unit often contains the control system for the actuator itself. The electronic power amplification element sometimes contains linear power amplification stages called servo amplifiers. In other cases, it may comprise power electronic drive circuits such as for motor-driven actuators. The variable conversion element serves the function of altering the nature of the signal generated by the electronic power amplification element from electrical to non-electrical form, generally in the form of motion. For example, electro-hydraulic servo valve, stepper, servo motors, current to pneumatic pressure converters etc. The non-electrical power conversion elements are used to amplify power further, if necessary, typically using hydraulic or pneumatic mechanisms. The non-electrical variable conversion elements may be used further to transform the actuated variable in desired forms, often in several stages. For example, motion to flow rate conversion in flow valves, rotary to linear motion converters using mechanisms, flow rate to heat conversion using steam or other hot fluids etc. Other miscellaneous elements such as auxiliaries for lubrication/cooling/filtering, reservoirs, prime movers etc., sensors for feedback, components for display, remote operations, as well as safety mechanisms since the power handling level is significantly high. Layer 1. Industrial Control Systems. Controllers are essentially, predominantly electronic, at times pneumatic, hydraulic, elements that accept command signals from human operators or supervisory systems, as well as feedback from the process sensors and produce or compute signals that are fed to the actuators. Control systems can be classified into two kinds. Continuous control sequence or logic control, continuous controller. This is also often termed as automatic control, process control, feedback control etc. Here the controller objective is to provide such inputs to the plant such that the output YT follows the input RT as closely as possible, in value and over time. Figure shows the common control loop with its constituent elements, namely the controller, the actuator, the sensor and the process. In addition, the signals that exist at various points of the system are also marked. These include the command, alternatively termed the set point or the reference signal, the exogenous inputs, disturbances, noise. The difficulties in achieving the performance objective is mainly due to the unavoidable disturbances due to load variation and other external factors, as well as sense noise, the complexity, possible instability, uncertainty and variability in the plant dynamics, as well as limitations in actuator capabilities. Most industrial control loop command signals are piecewise constant signals that indicate desirable levels of process variables, such as temperature, pressure, flow, level etc., which ensure the quality of the product in continuous processes. In some cases, such as in case of motion control for machining, the command signal may be continuously varying according to the dimensions of the product. Therefore, here deviation of the output from the command signal results in degradation of product quality. It is for this reason that the choice of the feedback signals, that of the controller algorithm, such as P, Pi or PID, the choice of the control loop structure, normal feedback loop, cascade loop or feed forward, as well as choice of the controller gains is extremely important for industrial machines and processes. Typically, the control configurations are well known for a given class of process. However, the choice of controller gains have to be made from time to time, since the plant operating characteristics changes with time. This is generally called controller tuning. Features of continuous control are controls analog continuous process variables, temperature, pressure, closed loop control, track, hold, set point, track if set point changes and hold if constant, reject disturbances, generic PID/special purpose tunable, implemented using dedicated digital real-time system, comparatively inexpensive, less than 5% cost of plant, sequence or logic controller. Many control applications do not involve analog process variables, that is, the ones which can assume a continuous range of values, but instead variables that are set valued, that is, they only assume values belonging to a finite set. The simplest examples of such variables are binary variables 1 or 0, on or off, open or closed. These control systems operate by turning on and off switches, motors, valves, and other devices in response to operating conditions and as a function of time. In the control of a conveyor system, analog motor control is not applied. Simple on-off control is adequate. Therefore, for this application, the motor starter actuation system may be considered as discrete, having 3 modes, namely, start, stop and run. A modern controller device used extensively for sequence control today in transfer lines, robotics, process control, and many other automated systems is the programmable logic controller, PLC. Features of sequence or logic controller are: control of discrete valued process variables, on or off control, high or medium or low control, discrete sensing, limit switch, pressure switch, photo switch, alarm. PLC or industrial PC or dedicated processor-based devices are used. No tuning needed unless control logic changes status or sequence or timing control is used. Level 2, supervisory controller. Supervisory control systems perform, typically, the following functions: set point computation. Set points for important process variables are computed depending on factors such as nature of the product, production volume, mode of processing. This function has a lot of impact on production volume, energy and quality and efficiency. Performance monitoring or diagnostics. Process variables are monitored to check for possible system component failure, control loop detuning, actuator saturation, process parameter change, etc. The results are displayed and possibly archived for subsequent analysis. Startup or shutdown or emergency operations. Special discrete and continuous control modes are initiated to carry out the intended operation, either in response to operator commands or in response to diagnostic events such as detected failure modes. Control reconfiguration or tuning. Structural or parametric redesign of control loops are carried out, either in response to operator commands or in response to diagnostic events such as detected failure modes. Control reconfigurations may also be necessary to accommodate variation of feedback or energy input, for example gas-fired to oil-fired. Operator interface. Graphical interfaces for supervisory operators are provided, for manual supervision and intervention. Level 3. Production controller. Various functions of production controller are process scheduling, depending on the sequence of operations to be carried on the existing batches of products. Processing resource availability for optimal resource utilization. Material handling, maintenance management, decision processes related to detection and deployment of maintenance operations. Inventory management, decision processes related to monitoring of inventory status of raw material, finished goods, etc. and deployment of operations related to their management. Quality management, assessment, documentation and management of quality. Typically, the algorithms make use of resource optimization technology and are non-real-time, although they may be using production data online. Level 4, Enterprise Controller. Enterprise Controller deals less technical and more commercial activities like management of supply, management of demand, management of cash flow, product marketing.